Hello everyone, welcome back to our thermodynamic class. Today we are going to learn the first part of Chapter 2, Description of Energy. Chapter 2 is for energy, energy transfer, and general energy analysis. We have two learning objectives. First, describe mathematically the rarest form of energy. Second, explain the nature of internal energy. As we learned from Chapter 1, there are different forms of energies. First, kinetic energy is denoted as Ke. The kinetic energy of a system is because its motion relative to some reference frames. Basically, the higher the velocity, the higher the kinetic energy is. The formula is Ke equals m times v squared over 2. Note that v is velocity. Don't be confused with the volume. For the kinetic energy per unit mass, we use lowercase ke, which equals v squared over 2 with the unit of kilojoule per kilogram. Potential energy, denoted as Pe, is the energy that a system possesses because of its elevation in a gravitational field. Capital P equals mgz, and lowercase p equals gz. Here g is the gravitational acceleration, and z is the coordinate of the elevation. Internal energy, U, is related to the temperature of a system and its other state conditions. More specifically, it can be referred as a sum of all the macroscopic forms of energy. There is no easy formula to calculate the internal energy. If we add all the energy together, it is called total energy. We can use the letter E to represent it. Therefore, capital E equals capital U plus capital Ke plus capital Pe. Again, the lowercase letter represents energy per unit mass. We can consider both kinetic and potential energy as macroscopic form of energy. The macroscopic energy is the energy a system possesses as a whole with respect to some reference frame outside. It changes with system's velocity and elevation. For example, a car with a certain speed and elevation. On the other hand, there are microscopic forms of energy, and the sum of such energy is called internal energy. Basically, the macroscopic energy is energy related to the molecule structure of the system and the degree of the molecule's activity. Here are some more details on internal energy. First, it represents the macroscopic state of a system or subject. The macroscopic states means the random motions of molecules, translation, rotation, and vibration, plus electron translation and spin or rotation. The structures of the molecules and atoms also represent a certain energy level. There are different types of the internal energy. Sensible heat is the energy due to the random motion of the molecules and the electrons. A system with a higher temperature means the random motion is stronger. Latent heat or energy is due to the forces between molecules. Compared to vapor, liquid has a stronger force between its molecules. Compared to solid, the force between the molecule of the liquid is weaker. For example, when liquid becomes vapor, energy is needed to overcome the stronger force between the molecule of liquid. This energy will become part of the energy for vapor. Therefore, vapor has more energy than liquid, even their temperature is the same. Atomic bond in a molecule represents the chemical energy. For example, when fuel is burned, the atomic bond in the fuel will be broken and then chemical energy will be released. In the meantime, the molecule becomes a different one. The highest level of the internal energy is the bond within the nucleus of an atom. If this type of the bond are broken, the atom will become a different one. In general, internal energy includes all these four types of the energies. When we talk about thermal energy, it means both sensible and latent heat together. The figures on this page can help understand the internal energy better. The left figure shows different types of the microscopic motion that make up sensible heat. For example, molecular translation and molecular rotation. The figure on right shows the state of the molecule in solid, liquid, and gas or vapor. Different levels of the forces between the molecule represent the latent heat related to phase change. The molecule in solid have a fixed position. Therefore, they cannot move but only rotate and vibrate. When the energy is at the end, solid becomes liquid. In liquid, the molecule can move but only around each other. Surely, they can rotate and vibrate. When enough energy is added into liquid, it becomes vapor. The molecule in vapor can move freely. The top figure on this page here shows how the chemical bonds are broken and different molecules are formed during the combustion process of the methane. CH4 plus oxygen results in CO2 plus water. Note that the element remains the same. During this process, chemical energy is released. The bottom figure shows the fission of the uraniums and the fusion of the hydrogen during the nuclear reaction. The fission turns uranium-235 into cesium-140 and rubidium-93 due to the addition of the neutron. The nuclear fusion turns hydrogen into helium. Surely, a lot of energy will be released during these processes. What we discussed so far is energy. Another concept is energy flow rate or energy rate, which means energy per unit time. It is especially important to a flowing fluid. For example, the flow inside a pipe. We know that the mass flow rate m dot is equal to rho times v dot where rho is density and V dot is volume flow rate. The volume flow rate can be further given by the area of the cross-section AC times the average velocity. For the energy flow rate E dot, it can be given by m dot times the lowercase e, which is the total energy per unit mass. Note that energy flow rate has a unit of kilojoule per second or kilowatt. Most of the students in this class are for mechanical engineer. Here is a question. What is mechanical energy? Mechanical energy is energy that can be converted to mechanical work completely and directly by an ideal mechanical device, such as an ideal turbine. For flowing fluid, the rate of the mechanical energy can be given by m dot times P over rho plus V squared over 2 plus Gz. We can also have the lowercase e mechanical, which represent the mechanical energy per unit mass. For incompressible fluid, which generally means the density is constant, the mechanical energy change from one state to another can be given by these two equations. These equations are important to calculate the maximum power output for hydraulic power plant or the minimum power needed for pump. This slide shows two different ways to calculate the power from a hydraulic power plant. In the first one, pumps 1 and 4 are taken as the reference. On the free surface, the pressure is the same as the atmospheric pressure, and the flow velocity can be ignored. Therefore, the maximum power will be m dot times g times h. In the second one, point 2 and 3 are taken as the reference, which are immediately before and after the turbine. The velocity is assumed to be almost the same at these 2 points, and the elevation difference can be ignored. Therefore, the maximum power will be m dot times delta P over rho. Although these are two different ways to calculate the power, the result should be the same unless very details are considered. Basically, this example shows how the mechanical energy is converted to work. Here is an example for practice. Water flows at a rate of 1,000 kg per second, and the elevation difference between the reservoir and the turbine exit is 10 meters. The water left the turbine has a velocity of 2 meters per second. What is the maximum power output? You can take 2 points. The turbine exit as point 1, the free surface of reservoir as point 2. Assuming the turbine exit pressure is the same as the atmospheric pressure, the power can be calculated by m dot times g times h minus m dot times v2 squared over 2. Please check your answer. Please note that the velocity difference only contributes a little bit to the power, especially when the elevation difference is big. That's all for today's lecture. Please let me know if you have any questions. Thank you. Have a nice day.